Hello, my friends. My name is Aditya, and today we are going to discuss P block elements. This is the second part of the discussion that we are doing on P block elements. In the previous part, we had actually discussed group 15, 6, 13, 14, and 15. And in this part, we'll discuss group 15, 16, 17, and 18. Okay. So just a few more general properties that we were stated in the previous lecture also, that firstly, what is the general electronic configuration of p block elements? NS2, NP126 can be that general electronic configuration. Okay. And today that we are going to discuss group 16, 17, and 18. So group 16 has NS2 NP4, and group 17 has NS2 NP5, and this one group 18 has the final complete octet NS2 NP6. Okay, these are your oxygen groups or the oxygen family that we talk. These are your halogens. Group 17 and group 18 are the noble gases that are present. Okay. Okay, then with this in mind, let's start the lecture. So we'll start with group 16. Now, group 16, which is generally known as the oxygen family, it has what? Oxygen, sulfur, selenium, tellurium, polonium. Okay. And the symbols are like here oxygen is O, sulfur is S, selenium is Se, tellurium is Te, and polonium is Po. Okay. Now, another thing that these are generally known as chalcogens, and they are found from ore forming compounds. These are the electronic configurations. We are not going to discuss that because I know that you know this. And if you have to talk about the metallic and non-metallic nature of this thing, oxygen we all know is a non-metal. Sulfur can exhibit both metallic and non-metallic properties at times, but most of the time we see it to be as a non-metal. And selenium, tellurium, polonium are proper non-metals, right? And as we go down, the metallic characters, sorry, this should be our primarily metals. But as we go down, we see the metallic character increases down the group. And this is just a thing of abundance. See a small part in the NCERT. And I would even like to say that always remember that when you are doing particularly inorganic chemistry, NCERT is your godfather. Okay. You have to follow this thing in that like it is your best friend over here. Okay. And so this is a small part from that. Abundance of oxygen is greater than sulfur is greater than selenium is greater than. It's a very basic thing. It's a normal logic. And melting and boiling points, if we talk in particular about it, both show a regular increase down the group. That is, both melting and boiling point increases down the group. And the basic logic of this is because the molecular and the van der Waals forces increases. So as our compound element starts getting more heavier, the melting and the boiling point should primarily increase. Okay. And now let's talk a bit about the oxidation states. So we have seen oxygen. Oxygen actually stores an oxidation stage of -2, -1, and 0 primarily. Okay, that we have seen in our chemical bonding chapter also. Same way sulfur. But the thing is, sulfur can go up to +6. And kind of like from sulfur all the way to polonium, this is what happens. Okay. And similarly, ionization energy is very high for oxygen, is large for sulfur compared to oxygen, and then it starts decreasing gradually. Okay, so just keep that in mind. And why does oxygen behave very oddly compared to all the other family friends of his? That is just because of his small size and his high electronegativity and his high ionization energy. So the things that everything is high, and that makes him, act very weirdly. And if we see, we have they show allotropy. Allotropy is basically multiple forms in a very layman's way. And you have O2, O3, rhombic and monoclinic sulfur, rhombic and monoclinic selenium, and everything. And just remember that these dudes even have a tendency of catenation. Now, what is catenation? Catenation is basically a method or a process by which the compound forms a chain with itself. Okay, so we have seen this thing in carbon. The whole organic chemistry is kind of like based on this simple thing that carbon shows catenation. And we see this even in sulfur, selenium, oxygen, and tellurium. Tellurium, okay? So, keeping all that in mind, let's talk about the oxygen's family's reaction. And first, I would like to start talking about its hydrides. So, the hydrides are H2O, H2S, H2SE, and H2TE, particularly. And if we see, this is a note about this from the Godfather itself, from NCERT. And basically, what it's kind of like telling us is that as we go down, the boiling point and melting point should increase, but we see that H2O in particular has it very high compared to all the other things that are present over there. And that, my friends, is just due to a simple concept of hydrogen bonding. We know that when we have hydrogen, oxygen, nitrogen, and fluorine, they tend to show a very high affinity or liking for a hydrogen bond when they see hydrogen around. And that is a very strong bond that is formed. So it is, to break that bond, you need a lot of energy. So the melting and the boiling points are pretty high. Okay. Other than that, if we see the angle reduces, which is a very common sense thing, same way the distance between the bond and basically the dissociation energy is also pretty high, and dissociation constants increases as we go down. Okay. And a few more things, that as we go from H2O to HTE, there is an increase in the acidic nature of the hydrides. And water exhibits unique properties. We have discussed about this point basically because of its hydrogen bonding. And we can even see that there is a very nice reducing property, because as we go down, the dissociation constant starts becoming bigger and bigger and bigger. Okay. Now, if we focus a bit on halides, right over here, I have just written that much. But actually, we have a lot of forms of halides that it can kind of produce, right? And primarily, it's like EX6, EX2, and EX4. Now, I know that it's a bit tough to imagine all that. So, we are going to consider E for the sake of this example to be sulfur. So, and X, let's just say, is fluorine. Okay. So, because SF is a very common compound that we have seen in chemical bonding also. So, we've seen SF6, we have seen SF4, and SF2 also kind of exists. Okay. So, my S is E is basically S in this example, and X is basically F in this example. Okay. And these are all compounds that kind of exist in the real world over here. So what happens is, we say that generally it's in the form of EX6, EX2, and EX4. Okay. And EX6 are basically our hexafluorides, and EX4 are known as our trihalides. Now, I just told fluorides because we are talking about SF6 in this case and SF4, but generally, this is what happens. Okay. And if we see all of them, here are a few things like, this thing has a hybridization of sp3d2 that basically leads to it having an octahedral geometry. And also that the geometry of all the SFs are kind of like discussed. Here they didn't use SF, they used Cl, but that's fine. It's kind of the same. And also just remember, selenium forms dichlorides and dibromides only. Okay. So that is a very, brief overview about the halides that are present for the group 16 elements, and a little bit of the view given by Godfather over here. Now, formation of oxides, and primarily the oxides are the most important part of group 16 when we talk, because we generally know more commonly the elements as oxides. So it has been a very, kind of a thing for us to know about them. Now, E2O3 or E2O2 are the two forms in which you see oxides over here, and both of them are kind of like acidic in nature, okay? And we have a lot of, like alpha, beta, gamma forms of these various oxides. And we have a few oxides to discuss. One is ozone, the other is sulfur dioxides and sulfur trioxide. Okay, so we have these three oxides that we have to discuss over here. So let's start with ozone. So ozone is basically used, right? We know ozone is basically present in our stratosphere as a ozone layer, and that kind of like protects us from, the UV rays and everything. And it's kind of like just formed from O2. What happens is you have O2 and the nascent oxygen kind of comes like here. And nascent kind of means a newborn oxygen. And that gives us O3. Okay. Now O3 structures is like this. And because that you can see there is a resonance over here. So this man actually lives in a hybrid structure. That is like kind of like this is the hybrid part. Like that, right? And there are many ways like UV rays on O2 gives the energy for nascent oxygen to combine, slow oxidation of phosphorus and reaction of fluorine with water and electrolysis of water at times can give it, and SO2 reacting with H2O2. But what is important thing regarding ozone is particularly that ozone is actually a very strong reducing agent, okay? So like I have showed over here, that there are four primary reactions when it comes to ozone. Okay, at times it could even oxidize, but most of the time you see ozone acts as a reducing agent, and this point has been highlighted in the NCERT also. And these are like the reaction. Basically, it becomes O2, it can decompose into O2, and it kind of like oxidizes, giving O2 and nascent oxygen. This should be nascent oxygen. And again, the reducing factor, you can see reduced water, H2O2, H2O2. And again, additional reaction like it's forming sulfur dioxide and everything that we know over here. Okay. Now let's talk a bit about sulfur dioxide. Now sulfur dioxide again has a structure like this. And obviously resonance is kind of like possible. At times what happens is you kind of attack the sulfur and the oxygen goes over here. But generally sulfur dioxide has this structure, right? And sulfur dioxide is also a very common oxide that we know that is present in group 16. Oh, and we have seen it, it comes out in volcanic eruptions and a lot of other places. And we know that it can cause some serious lung and breathing disorders. Now, there are a few properties of sulfur dioxide, basically that it also acts as a reducing agent, and you can pretty much cause a lot of bleaching using sulfur dioxide, and that you can, it has a reaction with KMNO4 to give MnSO4 and KOH. And you know that KOH is pretty much useful in a lot of analytical chemistry side of ours. And that is pretty important for us, right? So I'll just again remind you that I'm giving a very brief overview about a lot of things that is kind of like happening over here, right? And please go through the NCERT once also. This is just to highlight the important topics in inorganic chemistry. And yeah, so keeping that in mind, let's even look at sulfur trioxide formation. Okay. Now, sulfur trioxide, like sulfur dioxide, is also, another oxide of sulfur that is formed of in, the group 16 elements. And it is generally formed because of the heating of concentrated H2SO4 with P2O5. Okay, so this is actually a reaction in um, sulfur trioxide, and it has actually also obtained as a byproduct. And where is that obtained? As in contact process. And where is contact process used? Contact process is primarily used for the preparations of sulfuric acid, right? We know that, and we'll be discussing about it in a few. So just keeping that in mind, that you can actually use this as a byproduct is kind of like prepared in contact process. Okay, we will see about it later on further. And if we have to talk about a few properties of sulfur trioxide, it forms oleum with water. And if you have done contact process, you will know that oleum, that is H2O2O7. Okay, that is oleum, and oleum is a pretty important thing that is formed during contact process for the formation of sulfuric acid. And at that time, we use this man over here, this sulfur trioxide, and we hydrolyze this dude, and we get oleum, right? And this too has oxidizing properties, so it is an oxidizing agent, and obviously that it has sp2 hybridization, so it will have a planar trigonal geometrical structure. Okay, so now here you can see the structure of sulfur trioxide that is over here on the page. And you can see that at times when it takes place in bonding, you get um, charges, right? You get charges. So here are the charges. These are basically the formal charges. And yeah, so we have sulfur dioxide and we have sulfur trioxide, and that is kind of like the oxides of group 16 that are present. Okay. Now let's talk about a very important compound that is kind of like present in your NCERT also, and is very important for your exam point of view also, and that is basically sulfuric acid. Now we all know sulfuric acid, it is has a chemical formula of H2SO4, and that sulfuric acid is a very widely used chemical that we have, right? We use it in a lot of places in with a lot of purposes. For example, in organic, we use it in the process of dehydration, and for at times we can even use the reducing property of it, and at times even we can use it to produce a lot of things. So sulfur dioxide has sulfuric acid has its own importance in the chemistry world, and it is generally manufactured in two major ways. There was two ways to basically prepare this person. One is the lead chamber process, and one is the contact process. Okay, now the lead chamber process is a old process, and it's a bit messy also, and you have a lot of things like the Gay-Lussac's tower in this, which is this thing over here, or the Glover tower, that is this thing over here, and there's a purification of happening, and you basically get a lot of things. Okay, so basically what happens is kind of like both are very same. Okay, and what basically happens is that your air comes in and it gets burned with sulfur or purite burner, and then that creates goes into a dust chamber. Now this thing has hot gases in it, and hot gases in it, so it goes here, and here you can see you're passing water, so that buddy just cools down the entire thing in the lead chambers. The cooling kind of like happens in the lead chambers, and then what happens is basically you are sent this thing. These are sent out, and then it goes into your Gay-Lussac's tower. Gay-Lussac's tower, and then here the waste gases that are the unnecessary gases kind of like come out, and now all the gases that have been cooled are over here, right? These cooled gases are actually then bought into your formed over here, where you get a 80% H2SO4 solution over here, and you pour it from the top on these gases, and that kind of like causes your whole thing to happen. Okay, so there is a big mess on the screen because of the drawing. But overall, this is what happens. Okay, you start off, you get a gas that goes into the dust chamber, goes into the glow tower, and then the lead chambers. And basically, over there, the cooling of the gases take place. Okay, there are multiple layers of cooling, basically, in a very layman's way. And then it goes into your Gay-Lussac tower, where again it is you use H2SO4 to create H2SO4. Yes, that happens. So we create H2SO4 basically using H2SO4. Now, let's talk about contact process. So now in contact process also a similar kind of thing occurs, okay? So first what we do is we convert the sulfur dioxide that we have into sulfur trioxide, and that is a very easy step. Then what you do is you create oleum, right? Once you have oleum, then what you do is you dilute the oleum that is present over there. Okay. So we kind of like start with sulfur dioxide and oxygen coming together. And what happens is sulfur dioxide and oxygen, when they come together, they form our SO3. Right. Now what happens is that SO3 is kind of like passed into another chamber. Okay. So what happens in that chamber basically is that there we kind of form or think oleum. And now how do you form oleum? Basically what happens is you have a sulfur trioxide, right? So let me just write that reactions down. So the first reaction that you do is basically SO2 plus O gives rise to SO3. Okay. So this is what happens in step one. In step two, what happens is this SO3 is hydrolyzed. Okay. So when you hydrolyze this person, you get SO3 plus H2O. That gives you oleum. And now, remember, sorry, you don't hydrolyze it. I mean, you can hydrolyze it, but then what happens is you get H2SO4 over here, okay, during hydrolyzation. But what basically happens is that this process is exothermic in nature. Okay, because hydrolyzing sulfur trioxide is an exothermic reaction. It can evolve a lot of heat, and more the heat that is present, more it will cause fuming, and fuming will prevent this process from happening. That is why you can't use SO3 over here. So what you will do is instead of adding H2O, you actually add H2SO4 only. So again, you kind of like use H2SO4 to prepare H2SO4 over here. And this gives you oleum. That is H2O, S2O7. ठीक है? So H2S2O7 is basically what we use oleum for. And then what you do is basically hydrolyze oleum. So that is what overall view happens for a contact process. And in the middle, we use a catalyst called vanadium pentoxide, and that's primarily used in the conversion part of SO2 and SO3. And yeah, so if at times in present we are using contact process more profoundly compared to the lead chamber process. And yeah, so that means basically contact process is very much more important and valuable. And it is also observed that JEE tends to ask a lot of questions from contact process. Okay. So I hope that is clear. There was a bit of chaos during the contact process, but I hope it's clear to you. Now, a few more compounds. Basically, these are just a very, overview of these two compounds again. We have hydrogen sulfide and we have sodium thiosulfate. So, hydrogen sulfide basically, which is H2S, is prepared by adding dilute H2SO4, or you could even use HCl on iron sulfide. And what is iron sulfide? FeS, right? So we have FeS, and you kind of like add HCl if you want, or H2SO4, and that gives me H2S. Now, H2S is hydrogen sulfide, And the best characteristic that you'll find for it is it's a rotten egg smell. That's a very disgusting smell. And just remember that the gas is a that a gas is a poisonous gas. Okay, so don't just go inhaling it whenever you want. And similarly, this is also a reducing agent over here, because sulfur, is in a -2 oxidation state. So all it will do is oxidize itself. It will undergo oxidation to increase its oxidation number. So you can see that it is a very strong reducing agent because it's undergoing oxidations only. And along with that, we have another compound called sodium thiosulfate. And sodium thiosulfate is also a very important reaction, and it is generally even at times used as a reducing agent. So you basically prepare heating sodium hydrogen sulfide and sodium hydrogen sulfite. Okay, they are two things, and basically they come together, and that creates your sodium thiosulfate. Right now, sodium thiosulfate is not a very important thing compared to H2SO4 or sulfur dioxide and sulfur trioxide or your ozone. So if we have to talk about what you have to do, and yeah, that completes group 16 also, and it was a very small topic, group 16, but here, most of the questions that in P block, if they are asked, are generally asked from 15, 16, and 17. And in 16, particularly, if they are in a good mood, they'll ask you easy question from ozone, sulfur dioxide, and contact processes. And if they are in a bad mood, they could ask from the properties of ozone, from the properties of sulfur dioxide, sulfur trioxide, and from the some vital things that you pretty much use in contact process. Basically, you should know it properly. So because they can go up to the most minute detail that is present for that topic. Okay. Next, we'll talk about group 17. Now, group 17s are basically all our halogens. And again, I have like just taken the tables of this thing, and I would suggest you that take the NCERT on this again very seriously. The biggest parts of NCERT are group 15 and 16, obviously, and comparatively, group 17 and 18 are smaller. Okay, so that should not take much of a time in order to complete the topic. But however, I have tried to add as much things as I can. And let's get started with group 17. So again, they have a general electronic configuration of Ns2 Np5, right? And they become very highly electronegative. That is simply because it has five electrons in its outermost shell and it wants to get stable. So it has a high tendency to accept one electron, and hence you see that they are very reactive comparatively. And then also overview that group 17 are generally known as our halogens or halides that we have seen until now. So that has our fluorine, chlorine, bromine, iodine, astatine. Okay, so we have fluorine, chlorine, bromine, iodine, and we have an astatine, but we don't use astatine much. Okay, and our primary focus is most of the times on fluorine, chlorine, bromine, and iodine. Okay, so that is the thing over here. This is very basic slide. And here basically I'm just telling that we have group 17 elements, that is fluorine, chlorine, bromine, iodine, astatine. And fluorine and chlorine are gaseous. They are found in their gaseous form in the room temperature. Bromine is in liquid form. It is a brown color liquid that you can find. We'll talk about the colors also. And iodine is actually a very deep violet color solid, and astatine is radioactive. So they have not discussed about astatine much, even in the NCERT. Okay. Now, if we talk most of the halogens are diatomic in nature. I mean, all of them are, but yeah, you get the point. I'm telling most because we are not talking about astatine over here. And what happens is these things have their own respective characteristic color. Okay. For example, fluorine is pale yellow, chlorine is greenish yellow, yellowish green, bromine is reddish brown, and iodine is deep violet. Okay. And if you have done your experiments, then you will know that fluorine is a very deep brown liquid that is present over there. And fumes of that thing are also created while we perform our analytical chemistry. And iodine is a deep violet thing that at reaction, and sometimes, if it gets stained on your shirt, it kind of becomes yellow in color. So that is about iodine. And basically, the remaining are just the other property that the metallic character as we go down increases. And we know for a fact that all of these compounds are purely non-metals, right? And the oxidation state generally, fluorine only shows -1, chlorine can show -1 to +6, bromine can show -1 to +6, iodine can actually go up to +7, and that's the pretty cool thing about iodine. And astatine, even though we aren't going to talk about it, it shows from -1. It shows three of them basically: -1, +1, and +5. Okay. Now, again, the Godfather has come here to give us a bit of information about these things. So, like you can see, we talked about the few things that we talked about over here, that electronegativity actually decreases as we go down, and fluorine is actually even the most electronegative element of our entire periodic table, right? It has an electronegativity of 4. And similarly, if the radius goes as we go down increases, metallic character also increases, and ionization enthalpy decreases because fluorine is small, the electrons are slow, you need more energy compared to fluorine than if you consider iodine. Okay. Similarly, we generally see them in the form of F2, Cl2, Br2, and iodine, more rarely as fluorine, chlorine, bromine, iodine. And it's kind of the same over here. You see the density increases as we go down, that is from F2 to I2. And the bond dissociation enthalpy also kind of, has its own variance over here. Okay. Now, it should actually decrease, but fluorine, because of its extremely small size, it's actually causing a bit of anomalous behavior over here. But that is the whole story. Okay, that was actually summarized over here only. But this is the whole story as per it is discussed in the NCERT. Now, again, basic character increases as we go from fluorine to iodine, reducing also. So, you see, iodine is a better reducing agent than fluorine. And we have like the heat evolved during hydrations. Basically, that is more when it comes to iodine than it's fluorine. So that's a basic, order that it decreases from here to here. Similarly, if you compare it like with bonding with other elements, where M is just a random other element, so you can see that the ionic character is actually pretty high for MF, that is our metal, and basically fluorine. And the simple reason why is ionic character works on electronegativity differences. And as fluorine is the most electronegative element, it kind of has the highest electronegativity difference everywhere, right? Similarly, chlorine, then we have bromine, and then we have iodine. And metallic character we know decreases as we go down the group. So this fluorine dude is less than the iodine, chlorine, bromine, and iodine. That is basically the order. Now, if you want to form a hydra acid, basically HX, then just add H2 and X2 together. Now, X could be chlorine, fluorine. Just remember that when you talk about HF in particular, then HF actually even has hydrogen bonding with it. Okay. And that is what is actually discussed over here. We know that boiling point should is like kind of like proportional to your weights, right? The masses. But HF has a high boiling point just thanks to its hydrogen bonding that is present over there. And in the other things, if you see, HI is higher acidic strength because it is easier to give out, and H from iodine compound compared to from a fluorine compound, or even for the sake a chlorine compound, right? Because iodine has a very big size, and that thing, comparatively hydrogen and chlorine have a smaller size, so the bonding will just basically be better. And because acidic strength of Hi is very much greater than that of H FHBr and HCl. That's kind of the order that you follow for reducing character also. Similarly, the bond length, if we see, it is also the other way, like it's that kind of a thing, right? And basically, we have HBr. HBr is also a very important acid. We all know that. We have used HBr profoundly in organic chemistry, when particularly our Markov-Nikov and anti-Markov-Nikov's additions. Okay. Now, oxa acids, basically when you get like OX kind of things, then you know it's called the oxa acid. And there are basically hypohalous, halous, halic, perhalic acids, that in which you know you have a respective state of the halogen that you use. Like hypohalous always has +1 halogens. And similarly, this thing, halous acids have a +3 one. So there is a lot of different oxidation states possible for our halogens, and we know about that. And we are kind of like just using that kind of a property over here too. Okay. Now, if we talk about thermal stability of the acids, basically, as we go down over here, the stability increases, the acidic strength increases, and the oxidizing nature also increases. And also that if you hydrolyze halogen and X2, you can get an HOX. Now, we'll talk about oxides, even though oxides are not many people expect halogens to have their own oxides as at that same time. But we can talk about the oxides. So oxides, you can find AX3, AX5, and AX7, where these are the prime examples. Like you have IBr, BrCl. Sorry, these are interhalogen compounds, IBr, BrCl. And this is a property that you see only with the halogens, particularly the interhalogen compounds, where one halogen makes a compound with another halogen, basically. And there should be a pretty much size difference, because two atoms kind of like having the same size cannot form an interhalogen compound. And that also kind of, you know, there's a bit of a play of electronegativity here and there. And out of this, there are two, three reactions that you have to remember. So Cl2F2 gives rise to ClF3. And similarly, Br2F2 gives rise to BrF5. Okay. Now, if we just stop here for a moment and we discuss that what would a possible question, you know, if it comes from group 17, what could it be most of the times? Now, there are a few reactions that, come under the uses of group 17, which would have probably be done because what happens is, when our chlorine reacts with a few more things like, you know, sodium or calcium, right? So it forms very, you know, importantish compounds that are there, okay? Compounds that actually can do a lot of work. Particularly, I'm over here talking about NOCl, NaOCl, and obviously CaCl2 and CaOCl2 kind of compounds, and that those are important compounds, okay, when it comes to the play over here. So those ones, these reactions are generally discussed in the F block. So I'm assuming you have to know, but just for the sake, I'll write it here that you have an NOCl compound which uses Cl over here, and you have another compound that is CaCl2, and you have another compound that is CaOCl2. CaOCl2. Basically, how do you get this? You take NaOH and chlorine together. Okay, you take NaOH and you take chlorine together, and you'll kind of like get this. Similarly, if you take CaOH twice and you add chlorine, you will actually get CaOCl2, and actually you will even get this. Okay. Now let's talk about group 18 over here for once. So group 18 is actually very small. You have only two topics to discuss over here. One is this table, which tells from hydrogen to neon to argon to krypton to xenon, how all our things change. Like going down, the mass increases, the ionization enthalpy decreases. And to be honest, there is not a very big difference among these things over here. And that is primarily because our noble gases have a very stable electronic configuration, and they have a tendency to remain as stable as they can, so they don't react with anything. But similarly, if we talk about like xenon a bit, okay, so xenon is a very important compound because it kind of like forms complex compounds. It forms compounds. You've seen xenon oxides while we have done chemical bonding. You've seen xenon fluorides and chlorides and everything. So xenon is a very, a compound that we would want to have our focus on, particularly in group 18. So if you talk about xenon, it was actually founded, the first ever compound that was of a noble gas was actually found by Bartlett, and he made a complex compound. Basically, he reacted xenon with platinum hexafluoroplatinate, and that created a complex compound. And this compound that was formed was the first ever compound from a noble gas. So it kind of broke all the records that it had over there. And we have you can even see many compounds that of krypton now. However, helium, neon, and argon, still we have not seen any compounds of them. And radon, we know that it is used, it's because of its reactivity. And so the whole conclusion that we kind of like derive from this slide here is that xenon, it can form compounds, it can form complexes, there are reactions, there are compounds, and if for its assistance at times even krypton does so, but helium, neon, and argon cannot do it. Okay, now we have a reaction over here. Basically, what we do is we react Xc and F2 in different ratios. So when you see, if you take Xc and F2 in a 2:1 ratio, you get XcF2. If you take it in a 1:5 ratio, that is Xg1 and F25, you kind of get XcF4. And if you take it in a 1:20 ratio, you get XcF6. Similarly, they form a lot of compounds, this which I am assuming you have seen in your chemical bonding, the different types of compounds that it can form. And I'm assuming that I don't need to tell you why its hybridization is sp3d2 or sp3, because you have done it earlier when you did chemical bonding. And with that, we basically conclude the theory part of this. I mean, it is all complete theory, but I've got 6 questions for you people. And if we have to just wait a minute and like talk over here, what are the profound questions which are mostly asked? Again, it's mostly asked from group 15 and 16. If a question comes from group 13, it is generally on the AlCl3 or on diborane B2H6 kind of elements. And group 14, again, it's on mostly carbons, silicons, and silicates and everything. 15 and 16 are pretty important. Most of the questions that come from P block come from there. At times, you know, what compounds can form are asked from halogens about, and at times about interhalogen compounds. And at xenon, it's most of the times this particular thing that we just studied. And other than that, it doesn't ask much. So with that, I would just like to give you the first question. That is this. Reactions of organic sulfite X with dilute H2SO4 generates Y. Y gives X again when it reacts with NaOH. Okay. Further reaction of X and Y and water affords compounds X compound Z. So you're asking Y and Z. Okay, so here's the thing. You take X, which is a sulfite, and you kind of like get reacted with H2SO4 to get again a thing. Let's say X plus H2SO4 gives Y. Now when you add Y plus NaOH, you get X. Okay, that is a very funny thing. And then you are adding X plus Y in water and you are kind of like getting a Z. Okay, so if you people know, when you add sulfur trioxide, right? The SO3 part, remember, wherever you see it. So if you take an SO3 and you add it H2SO, you kind of like get oleum. Now you add NaOH, you kind of like will I'm assuming from with this SO3 because you're adding NaOH and you're kind of getting that back. That would be NaSO3. Okay. Na2SO3 is the correct compound name. And along with that, now they are asking Y and Z. So as soon as you have got Na2SO3, we can clearly find. See, Na2SO3 plus H2SO4 is basically SO3 2 minus and H2SO4, which kind of like gives H2SO4 because it has a reducing property and reducing property basically would have made SO3 to SO2, right? So we'll get SO2 as Y. So it's kind of either A or C. It's clearly not B and D. Now we have to see with Z. So what happens is now you will get Y, and Y is kind of like sulfur dioxide. And basically, and we kind of figured out that Na2SO3 will be my X. So we have Na2SO3 and we have SO2 and we are adding water, and this thing basically gets what? NaHSO3 bisulfite. So this correct answer should be C. Okay. I hope you understood that. And similarly, I this is the reactions over there that are particularly included, all of the neat reactions. Along with that, next question is this. Boiling point of H2O is this and the boiling point of H2S will be. Now, we know that the boiling point of H2O is kind of the maximum. It's the most over there. And that is just thanks to the hydrogen bonding that H2O shows. And that is why it will be less than 300 K. We have seen that a rough value, right? It'll be less than, it can't be equal than 370. It can't be more than that. And it has no way to be over here because we saw the values were in 200. And that is kind of like the reason that we have seen over here. Okay. Next question. Nitrogen and oxygen are main components in the atmosphere, but they do not react to form oxides. And the reason for this is reaction between nitrogen and requires a high temperature. Now you have to just tell is both of them correct and if one is the reason of the other. But now see, we know that reaction between nitrogen and oxygen is a high temperature because N2 and O2 are pretty stable. Okay, so this is kind of a reason is correct. Nitrogen and oxygen are main components of the atmosphere. That is correct. But is the reason an explanation? This pretty much does not need an explanation of why the oxides are not formed properly. So and I mean, yeah, this is a pretty, this is a pretty accurate explanation because they are pretty, they need a pretty high temperature to react with each other, and that is why that is there. So the assertion and the reason are correct, and the reason is the correct explanation of the assertion, and that should be your option C. Okay. So I'll just show you the solution also that it gives. Pretty much theoretic, everything is theoretical over here. And this is the solution. You can read it later when we do the slides. Now we have this reaction. And we just discussed this. This will actually be NaOCl and NaCaOCl2. We just discussed these reactions. So this clearly will form option A. Okay. So yeah, option A. That's this. And that's the thing. Now, again, the correct order of thermal stability that we talk about over here. And we know for halides, a thing is that the bond strength as we go down decreases. Now, as the bond strength kind of like decreases, you can easily tell that it becomes more easily breakable, the bond. And that is why we know HI has a high acidic property. So this is a very simple question. It's actually directly C. Thermal stability is very much proportional to the bond strength, and we know that HF has a very good bond strength, and that's Cl in the H. And that is pretty much the reason over here also. And in the end, they have given a bit of numerical values over here too. And next, xenon hexafluoride, and that is basically your XCF6. On partial hydrolysis gives two compounds, X and Y. Okay, so this is a reaction that was not in the slides. And what happens in this reaction is when you hydrolyze it, it has two things, okay? It gives you two major compounds. One is XCO2F2. Okay. Let me just write that here. One is XeO2F2, and the other compound that we actually get is XeOF4. So I'll write that here. XeOF4. Now this man is formed under partial hydrolysis. And then when you take this man and again hydrolyze him, you'll get this dude, XeO2F4. Okay, and you can pretty much calculate the oxidation numbers. These are actually pretty simple compounds to calculate the oxidation number. XeOF4 has a +6 oxidation number, and even XeO2F2 has a +6 oxidation number. So that is option C. Okay, so let me just clear this screen and show you the solution. And that is pretty much the solution over here. So with that, we have completed group 16, 17, and 18 in the P block. And I would again just tell you that please see the NCERT for this. Okay, so let me just write it on a blank screen here. Please refer to the NCERT. Because we have just given a very brief overview about what are the important things and where they generally ask the questions from, with a slight explanation of those important things only. And it is really advised that you kindly do the questions and in your reference books, and make sure you do the NCERT questions also, because NCERT has pretty decent questions when it comes to inorganic chemistry in the back. Okay, that is more than enough. So with that, I shall conclude this session, everyone. Have a great day and thank you.